Hello, everyone, and welcome back. This is lesson 4.5, continuing and getting towards the end of Unit 4. We're looking at applications of quadratic functions. So if you think about the previous lessons, we've learned about vertex form and factored form and standard form. We've learned about completing the square, imaginary numbers, solving quadratics, all these things, right? We're taking all of that and now applying it to real-world situations, right? Because quadratics model a whole bunch of different things that you can both see in the real world, but also that help us interpret things that are happening. So there's some examples. In fact, I'll actually talk about this for a moment since it's right here. The types of problems you might find in this unit are how do you see parabolas physically, right? So sometimes, and this isn't true for all bridges, but some bridges might be built parabolically, right? Here's my little cars. Well, okay, those are people, I guess. But yeah, so it's a bridge that's put into a parabolic arc, right? And maybe even some cables hang, right? Perhaps you're supporting a bridge like this, right? So maybe the bridge is down here. You ever see one of these, right? And perhaps the way that this cable hangs, perhaps that is parabolic in shape, right? We also have what's called projectile motion. So if you've ever thrown anything through the air that's aerodynamic, I might be here and I might throw a little ball and it would go up, and then it would come down, right? And this parabolic shape is caused by Earth's gravity. Because everything's going to fall back to the ground. And what's really cool and neat is when you throw it, it's pretty much always a parabola, unless you have like external factors affecting it. But if you throw it in a vacuum with no factors, it's going to look exactly like a parabola. But we can also use parabolas in an abstract way, and maybe you can read those. But an example of what I mean by abstract is perhaps there is perhaps I'm selling an item for some price and I generate revenue based off that price. Sometimes, it's not always true, but sometimes a parabola might model the revenue function, right? So like if I sell it for really cheap, right? I don't make a lot of money. If I sell it for really expensive, few people buy it, so I don't make much money. But there's an ideal price point that if I sell it, I maximize revenue, right? And that'd be like the vertex of a parabola. So it's things like that, right? That maybe you don't see with your eyes, but they can model the way things grow or decrease, increase, decrease, that kind of thing. Okay, so I want you to keep these three things in mind. I would star all of these when you're working through these problems, because really the main goal is if you know all the techniques we've learned, if you know how to find the vertex, if you know how to factor, all this stuff, right? All you have to do is connect those techniques with what the problem requires, right? Or what the problem's interested in finding. So there's really, with parabolas, 2 or 3 things you're kind of looking for. Number one is, what's the minimum or maximum? That's just the vertex, right? You're interested to see what's the highest point of this curve, perhaps what's the lowest point on this curve, right? Where does the function equal 0, right? So like, we talked about projectile motion. If you're up here and you throw something, well, then when it hits the ground, that would be like 0, right? And so that'd be just finding the roots. We've talked about how to find roots, and there you go. And then one other thing to keep in mind is, what is your reasonable domain and range? For example, perhaps I'm like I just said, I'm on a cliff and I'm throwing something off the cliff. It falls like this. Well, my domain and range, the range would keep on going like that, and then the domain would be spreading infinitely backwards like this, right? And so that's maybe not realistic, because it's really just this piece of the curve that we're actually seeing with the object, right? So just something to keep in mind. Okay, let's go ahead and get started here, do some actual thinking and examples. But the techniques you want to remind yourself of and connect from previous learning is, if you're trying to find the vertex of a parabola, right? you're trying to maximize something, you're trying to find highest height, right? Look for those words, minimize, maximize, right? Or anything hinting towards that. Then you're just trying to find the vertex, and there's two ways you can do that. You can complete the square. Oh, I misspelled complete. Let's say complete the square. Oh, okay. Mr. Spade cannot spell today. The square. And then there's also a shortcut, and the space is a little tight right there. So I'm going to zoom in for you. Use h equals negative b over 2a. This is a shortcut we've talked about in class, right? And then find k equal to f of h. And just a quick reminder of this technique, what this is a vertex is the point h comma k, right? So this vertex is hk. So you can find the h value by taking negative b over 2a in standard form. So if you had ax squared plus bx plus c, standard form, if you do negative b over 2a, that tells you the h value. How do you find the k value? How do you find the y value at that height, right? Then you say, oh, well, y equals all this. So you take whatever you get for h and you plug it in for x, right? And then you evaluate that, and whatever that comes out to, that's the y value, that's the k value, yeah? That's just a reminder of that technique. Okay, but then maybe I'm interested in finding the roots, right? Maybe I'm interested in finding where a parabola hits the x-axis somehow, right? Hitting the ground or canceling it, right? Maybe I have a revenue function that makes no money, right? I'm looking for when is the quantity I'm interested in going to be 0, right? Because that's what a root is. It's what makes y equals 0. So I could try factoring. This is, when you work with real world situations, it's going to be a little rare that factoring works, but, sometimes the word problems are more of a thinking exercise than an actual realistic thing. So, maybe you can try solve by factoring. You could solve by completing the square. We've talked about that. If you can complete the square, you can put a vertex form, and if you put a vertex form, it's very easy to solve from there. Or as an alternative to completing the square, you could use quadratic formula. And I'm actually going to recommend that when it comes to word problems like this, quadratic formula is probably my go-to, unless factoring's like really nice, all right? But we'll see that as we go on, okay? Okay, let's get into some actual problems. We've got 3 problems in this video, and they're all talking about different types of things you might encounter, okay? I want to note before I start, this is not 100% comprehensive of the problems you're going to see on the homework. So you might say, Mr. Spake, you didn't cover a revenue cost function in the video. How am I supposed to do the homework? And I would say, you have a brain. Yes? This is your brain. This is you. Here's you. Happy you. Let's say make this very happy. It's a very happy you. There you are. And this is a X-ray image of your brain. Yes? So just because I don't talk about it in the video, you can think about it. All you have to do, I'm modeling techniques so you can see how to think about and approach these things. But some of the problems you encounter on the homework, you're just going to have to think about it, right? My recommendation, draw a picture and really interpret how a parabola is used to identify and connect this information. Because if you can get a parabola, you can find points on a parabola, or you could find an equation of a parabola, then you've got it from there. Yeah? Okay. So there's our brain. Okay, example 1. Projectile motion, height versus time. So this is, when you say projectile motion, this is referring to throwing something. So here I am, and I throw something through the air. Yeah? Now, it says height versus time. So actually, this visual here, that visual encapsulates distance and height. And you see, that's actually not what this problem is going to be about. It's going to be about height versus time. So the x-axis is actually going to be time, and the y-axis is going to be height. And a parabola will still model projectile motion this way, but it's not a visual that you see, because time, this x-axis as a time dimension, you're not seeing time, right? Time's just happening. You are seeing the height, though, so there's a bit of a visual connection there, but it's not the exact picture of what's happening. So, if you plug it into a calculator, you see the graph, you might say, well, this looks a little weird. I don't think this is actually what it looks like in real life. And you say, well, that's because it's not what's happening. It's not what you're seeing. Yeah, it's a model. So, okay, here we go. Let's read through this problem. This is a type of physics problem you may encounter. But in physics, you're going to talk about vectors and direction. I'm not going to get into that. So it says, the formula h of t is negative 4.9 t squared plus v naught t plus h naught models the height h of a bottle rocket in the air t seconds after it takes off, where v naught is the initial velocity and h naught is the initial height in meters. Whew. Okay, first of all, I'm gonna pause there. What is he saying? V with this little zero, I'm saying this is v naught. Yes, naught. You say, oh, it's all for naught. It's all for nothing. It's all for, zero, right? So it's pretty common to call this V0 or V naught. Yeah? Okay. And what this means, this symbol, you'll see it a lot in physics, chemistry, the sciences, right? The zero usually refers to initial, the starting value. So V naught implies initial velocity. It's how fast it's going the second it's launched from the air, right? And then h naught is the initial height. It's the height at where it was launched, because maybe it was launched at ground level, or maybe it was maybe it was above a ground level when it was launched into the air. Okay. Answer the following, given that a rocket has an initial velocity 9.7 meters per second and is launched off a platform 0.5 meters tall. So, first of all, let's just label that information there. Initial velocity of 9.7, that's v naught. And launched off a platform 0.5 meters tall, that's h naught, right? That's how fast it's going at first, and that's how far the platform was up off the ground where the rocket was launched from. So it's the initial height. Okay, so part A, what is the maximum height of the rocket above ground? Okay, interpreting that, maximum height, well, if, like I drew earlier, my parabola is time versus height, and this is making, some sort of parabola, then it looks like I'm interested if the maximum height would be the tallest height, which happens to be the vertex. So all I need is a standard form equation and then find the vertex from that. And you say, well, where are you going to get the standard form? Well, it's given right here. Look, h of t is negative 4.9 t squared plus v naught times t, but we labeled v naught as 9.7, so I'm just going to put that right there, plus, and then h naught is 0.5. Hooray! So this is my standard form equation, and from this, I need to find the vertex. Now, we could scroll up, and we could say, oh, if you want to find the min-max of the vertex, you could complete the square, or you could use the shortcut. And if I look at this, I would say, complete the square? I don't want to do that. That's terrible. I don't want to factor out negative 4.9 from t squared minus, whatever that is, right? Terrible, awful, disgusting. No, I'm not going to do that. I'm going to do the shortcut. So I'm going to say this. Okay, now something to mention. I will say traditionally, but usually the vertex is written h comma k. I'm going to avoid using h because h is height. Like this is like my y and this is like my x. So x is t, y is h. So here's what I'm going to say. T, the shortcut is, if you want to find the x-coordinate of the vertex, you say t is negative b over 2a, right? And when we say negative b over 2a, we're referring to A, in this case, t squared plus bt plus c, like that. So plugging this in, negative b would be negative 9.7 over 2 times negative 4.9. And you can calculate this and get something. It looks like it's going to be about 9.7 over 9.8 if you kind of clean that math up. And so this is something you can type into the calculator. Because on most of these problems, you're going to be given a calculator to do these. Because we're interested in, it's a real world problem. It's going to be hard to do it by hand. So here's what I'm going to do. I'm going to show you a technique. I'm going to take this and store it in my calculator because I want the exact value, 9.7 over 9.8. I'm not going to round that. So here's how I do that. Where's my calculator? Right there. Okay. Awesome. Oh, were we working with logarithms? What the heck? Hello? Oh, it's an ad. Let's go. What? Hello? What is happening? What is happening? Skip this. Restore. What? Hello? Get me out of here. Oh, that was a remove ads by going, no, just don't tease me like this. Oh, in a quiet place. Okay, well, now you have ads in the video. I apologize. This was my intention. Anyway, we have 9.7, so I'm going to say alpha x. So I say 9.7 over, 9.8. And then I'm going to click the store button right there. And I'm going to store this for x. I'm going to say enter. Nice. So if you see that decimal there, the calculator is going to store that value for x. And now, actually, let's make a note of this. I'm going to round it just for the sake of seeing. 0.9897, let's say 0.9899, right? Let's call that roughly 0.9899 seconds. Yeah, because this is t for time. So this has not found the maximum height. What this is saying is 0.9899 seconds after launch, the rocket will be at its maximum height. So how do I find the maximum height? Well, I take that t value and I plug it back into the function. So this function, negative 4.9, blah, 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 I'm going to just type this in my calculator. Negative 4.9, and I'm using x instead of t. Whoa, what the heck? Graphing plus, I don't know what that is. Plus 9.7x plus 0.5. Okay, that's great. Thank you. But hello? Does this calculator not do that? Lame. Okay, children. One moment. Mr. Spake has not really... I wish I had a real TI-84. Okay, 9.7 divided by 9.8. Let's store that for a letter A, okay? Then I'm going to say negative 4.9 a squared. What the heck? 4.9 a squared, 9.7. You can skip this, by the way, children. Oh, my goodness. Mr. Spake is losing it. Plus, there it is. There it is. Okay. So I guess I didn't want to graph it, okay? I didn't want to graph in the calculator. I wanted just to get this value. So I stored it for A instead of X because this calculator was doing that, okay? Also, it looks like we can get a power high demand appliances with 4,000 wattage on Black Friday sale. I don't need that. Okay, so seeing this, there is, I just highlighted in pink, that's my answer. 5.3005, I'm just going to call it 5.3, right? And so what that tells me is the height. So if I say h of t, or I've used this new t value, this is 5.3 meters. And that's the maximum height. I feel like that took a really long time. I'm sorry about that. It's not that hard of a question to answer, really. You have the equation because it's given to you. You use the shortcut to find the time that it takes to reach the highest point. Then you take that time, you plug it in to the function, and then you get the height, and that's it. And that is the value of the shortcut because I don't want to complete the square. That was not going to be fun completing the square on, right? Okay, let's answer part B. It says, how far above the ground is the rocket 1 second after launch? How about after 3 seconds? So what this is asking is, my function's h of t. I'm just looking for when t equals 1 second and when t equals 3 seconds. So I'll say h of 1, and then I'll look at h of 3. And what's nice is I already typed this into my calculator. I could go to my calculator here. I could say 1 stored for x. 1 stored for x. Using a. Right? And I get this. And then I'll just copy this and click enter. So notice what I've done calculator-wise. Also, it looks like we have Sunday night football on Peacock. I should be getting ad revenue for this, but I am not. So I stored 1 for a, and then I just copy-pasted the same equation, and that replaces the a value with 1 because that's what I'm evaluating it at. And I get exactly 5.3, right? So I get 5.3 meters. Remember that the previous answer was also 5.3, but it was technically 5.3005 something, right? And this makes sense because 0.9899 seconds, that's basically 1 second, isn't it? We pretty much already found this if you kind of round it a little bit there. Okay, so that's where it is 1 second after launch. Where is it 3 seconds after launch? So I'll go back to my calculator. I say 3 stored for A. Now we have a top choice for auto carrot lambs. Just doing all sorts of advertising today. And then I'll copy paste that and I get negative 14.5. So let's write that down, right? When I plug in negative 3, I get negative 14.5. No, wait a minute. Oh, is someone here?
Yes, it's me, Andrea.
I'm filming a video.
I know, but close the door.
Okay, that is my wife, Jocelyn. Hello.
Here.
Okay, let's get back to it. So, negative 14.5 meters. She has a friend over. Okay, she's unannounced. I did not know they were coming here. Sorry for the disruption. Man, this video is just full of disruptions, but I cannot stop now. I will just make sure I stay on task. So it's negative 14.5, right? And so if you're thinking pictorially about this, right, this is suggesting the parabola is coming down here. So at 3 seconds, it's negative. But wait a minute. What? I launched this little bottle rocket, which is not very heavy or fast. Well, it's a little fast, but it's going to come up like this and then down. It's not like an asteroid hitting Earth. It's not going to go down beneath the ground, right? So this answer doesn't make realistic sense, right? If you said, 3 seconds after launch, the rocket is underneath the ground, you would say, we're standing in a parking lot. What? That doesn't make any sense. You would say, actually, the way I'm going to interpret this, I'll say, no, this tells me that at 3 seconds, it's 0 meters. It's at ground level, right? It was launched and now it's hit the ground, okay? And that's it. So it's 0 meters, and we applied real reasoning to that. Okay, last one says, at what time does the rocket hit the ground? So again, if you're looking at our model that we drew over there, when you say, when does it hit the ground? Well, that would just mean that the height is 0. So that's essentially saying h of t equals 0. You're finding the roots. You're finding the zeros, the x-intercepts. So you say h of t equals 0. That just means you're looking for whenever negative 4.9t squared plus 9.7t plus 0.5 equals 0. And you say, Mr. Spake, how am I going to do that? And I say, well, you could factor, terrible. You could complete the square, terrible. Or, because we have our calculators with us, why don't we just do quadratic formula, right? So we'll sing the song. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now look at that. Amazing. Takes you so few seconds to recall this, right? So x equals, and I'm going to put in negative 9.7 plus or minus square root of 9.7 squared minus 4 times a times c all over 2a. And if you have no idea what the heck I'm doing, then you need to go look at quadratic formula, because that's just plugging numbers in, right? It's ax squared plus bx plus c. So I'm plugging in this for b, right? And so forth. That for a, that for c. Okay? This is something I'm going to type into my calculator and see both answers. So try not to take eons to do this. Negative 9.7 plus square root of 9.7 squared minus 4 times negative 4.9 times 0.5 all over, all over 2 times negative 4.9. Enter. Yes. Okay, so I get negative 0.05. Okay, so that's my first answer here. So one answer I get is that this equals negative 0.05. And then the other answer that I get is, well, I'm going to copy this and then replace the plus with a minus. Sometimes students ask me this question, how do you do plus or minus in the calculator? You don't. You just choose one the first time and then you choose the other the second time around. Yeah? So I'm just doing plus and minus separately, and then I'm getting this answer here. So the other one I get is about 2.03. I'm just going to round that, 2.03. And so now let's interpret these answers, right? It says, at what time does the rocket hit the ground? Well, this tells me, next question. This tells me at negative 0.05 seconds and at 2.03 seconds. Now, naturally, we're going to say, well, time's not negative, so I'm going to x-nay that, right? I'm going to say, okay, that doesn't make sense. And then I'll box this, and this is my answer, right? So after about 2 seconds, that's a really fast time. That rocket didn't go very far, I guess, huh? It just went, right? 2 seconds, and it's done. Its flight path is over. So I went, okay. But what the heck is the negative point? What does that even mean? Where is that coming from? Why is that? Like, yes, I'm going to reject it because time's not negative. But why am I even getting that in the first place? And you think, well, based off the picture, the initial height was right here. And we threw it up, or well, it got launched up and then it fell down to the ground. So at about 2 seconds, that's when it hits the ground. The 0.05, the negative 0.05, is this piece coming down here, right? So that's the other root, but graphically, this didn't happen, right? It was at time equals 0, it was launched above the ground, so that left x-intercept is not really what happened. Okay, cool. And so that is that. Nice. Let's move on. Example 2, projectile motion. Oh, again? And I say, yes, again, except this one is about the path of an object. So in the previous problem, we did height versus time, but here we're going to look at distance versus height. And the reason this is different is because this is the visual parabola you're seeing. See our little basketball player here. He's throwing a basketball. It is going to follow a parabolic arch towards the hoop right here. Okay? So this is a physical parabola you're seeing happening in real time. If you could take a picture of the ball every moment it was flying through the air, you would see a parabola, right? So let's try and answer some of these questions now. It says a basketball player throws the ball towards the hoop, and it follows a parabolic path through the points below. So those points, what this is essentially saying, right? So like 2, 10 means I'm going to call the basketball player and where he's throwing the x-axis. We'll call the ground where he's standing. That's the y-axis, right? And then this is x. So this point means, right? It's 10 feet above the ground, and it's 2 feet away from him. Yeah. And so on and so forth. 4 feet away from him, 12 feet above the ground, 10 feet away from him, 12 feet above the ground, right? And it says to write a quadratic function in standard form that models this. Well, just think about this. Standard form, 3 points. Standard form, 3 points. And we've covered this in lesson 4.1. If you have a function in standard form, ax squared plus bx plus c, and you say this equals y, right? Then the way I can find a standard form is by doing matrices, right? So I can say, okay, let's pick 3 points. The first point is to 10. And so you plug in, these are all x, y. So you say x is 2. So it's a times 2 squared. 2 squared is 4. Plus b times 2 plus c is the y value, 10. And then you do 4 comma 12, and you say 4 squared times a is 16a, plus 4b plus c is 12 is the y value. And then the last one is 10 comma 12. 10 squared is 100a, plus 12b plus c is 12 again, right? If you have no idea what I'm doing right now, you probably want to go watch 4.1. It's at the very end of it's the last example in that video, okay? But this is a method we've learned to take 3 points, use a matrix calculator, and then that will tell you standard form, okay? And to anyone who is not my student at Cedar Ridge watching this video, you might say, or perhaps you are a student, whatever. A student might say, couldn't you just do a quadratic regression? And I say, yes, you could, right? But for context, I have not taught my students how to do that because they probably learned it in Algebra 1. Okay, so let's make a matrix out of this. Actually, do you guys remember that? Do you remember doing that in Algebra 1? Okay. 4, 2, 1, 10. This is augmented matrix that we learned in Unit 3, like this. And so this is the matrix you're going to plug into your calculator, and then you'll get row-reduced echelon form, right? And what that's going to do is it's going to give you your calculator's going to spit out row-reduced echelon form with A, B, C right here. Okay, so whatever those numbers are going to tell what A equals, what B equals, and what C equals. So calculator time. I'll try not to take too long with this. Again, if you don't want to see calculator junk, you could just skip through this, right? 4, 2, 1. What the heck was it? 10? No way. Yeah, I think it was. And then 16, 4, 1, 12. 100, 10, 1, 12. I believe that was it. I'm sure hoping. Second quit, second matrix, nope. Second matrix, math, row reduced echelon form. There it is. All right, cool. Negative 0.125, which you might recognize as 1/8, right? Negative 0.125, 1.75, and 7. So A is negative 0.125. Okay, honestly, I forgot it. What was it? Is that 1.75 and 7? Okay. 1.75. 1.75 and 7. So your standard form equation is y equals negative 0.125 x squared plus 1.75 plus 7. Nice. And notice, we haven't even answered any questions. Oh my gosh. That was the setup to the problem. Goodness gracious. Okay. Suppose the basketball hoop. Oh no. Suppose the basketball hoop is positioned 13 feet horizontally away from the basketball player and adjusted 9 feet above the ground. Essentially what this is asking is the hoop itself, or the poop, is 13 feet away horizontally, 9 feet above the ground. Does the player make the shot, and how do you know? I said, well, so he's going to throw the ball, and I guess what we're looking at is that we're following the path of the ball, and it's either going to go through that point or it's not, right? So how do you evaluate this? I said, well, if the hoop is 13 feet away and it's 9 feet above the ground, then when the basketball is 13 feet away from the player, it should be 9 feet above the ground, because that would be meaning it is going through the hoop, right? So what that essentially means is I want the point 13.9. So I see, does h of 13 equal 9? Question mark, right? This is what I'm interested in. Why did I say h? I guess I said h because you could say y. You could call that h of x. Sorry, it's just habit. Height depending on distance, right? So does h of 13 equal 9? Well, that just means to take our function and plug in 13, right? There's an x here. Sorry, there was an x here, okay? 1.75 times 13 plus 7, like so, okay? And I just want to see, does this equal 9, question mark. So calculator time, negative 0.125 times 13 squared plus 1.75 times 13 plus 7. I get 8.625. 8.625. Hey, 8.625 is not equal to 9. Therefore, right, and if you think about it, that's lower than 9. So I think if you were to actually draw this parabola of the basketball, it would have missed the hoop, right? It would have been below 13 comma 9, because it's 13 comma 8 point something, right? So no, he missed. We didn't get 9, and therefore it doesn't work. Alternatively, you could set the function equal to 9 and use quadratic formula to see if h was 13, but that's harder, so I'm not going to do that way, okay? What is the maximum height of the basketball? I said, well, we did that. We did that on this page. What's the maximum height of the rocket? It's the shortcut. That's what it is. So that's what I'm going to do here, right? The maximum height's going to be right here. So it's got to be between 4 and 10, right? Or it's going to be higher than 12 feet. So I say h equals, I'll just say x equals negative b over 2a. And what that is negative b is negative 1.75. By the way, my eyes are looking right here. That is where my eyes are. That's b, that's a. So negative 1.75 over 2 times negative 0.125. Calculator time. Sorry, calculators don't work well for videos, which is actually why I've kind of put off filming this video for a moment. Negative 1.125. Is that it? 7. Is that it? 7? Exactly? For real? Hold on a second, because I have questions. This is 7/4, and that's 1/4. Oh, yeah, so that is 7. Neat. Okay, cool. So x is 7, but that's not the maximum height. What that means is the maximum height is going to occur 7 feet away from the player. Okay? So to find that height, I'm going to plug in h of 7. Okay? That means it's this function, but replace the 13 with the 7. So go back to my calculator. I'm going to copy that, but then I'm just going to go change that 13 to a 7. Also, what is this? Rosa's Cafe. Okay, so again, with the advertising, perhaps you can dine in or drive through. Oh, in Cedar Park, that's where I am. Uh-oh, wait, don't dox Mr. Spake. Don't say that. Okay, not Mr. Spake's not in Cedar Park. Ooh, it is not the case. Okay, 13.125. 13.125 feet. Okay, Mr. Spake is not in Cedar Park. No, you're hypnotized. No, he's not there. You do not know where Mr. Spig lives. He is not living near Rose's Cafe in Cedar Park. Okay. And so that is the height above the ground. That's the maximum height, about 13 feet. 7, comma, 13.125. Okay? All right. Lastly, if the basketball hoop was adjusted to be 10 feet above ground level, then how far would the player need to stand so the basketball goes in? This is probably the toughest question of these three, I'd say. It's a little tricky because what it's asking is, suppose that the hoop is 10 feet above ground level, right? So this is x comma 10. Then where would the guy need to stand? Would he need to stand here? Would he need to stand here? Would he need to stand over here, right? And actually, all of these are going to be our y-axis. We don't know where he's standing because the path of the ball is going to be the same arch, assuming it follows the same arch, right? So, what does this mean? It means your function h of t, or not h of t, but h of x, your function h of x needs to equal 10. So negative 1.524 squared plus 1.75x plus 7, this needs to equal 10, right? So you're saying what x value makes this happen? Well, am I just going to take a calculator and just guess until I get 10? No. What I'm going to do is, the way we can solve quadratic equations, as we learned in the previous lesson, is set the function equal to 0, right? Because if you can set an equation equal to 0, you can use factoring or quadratic formula to find the zeros of that. So, minus 10 from both sides. Because the goal here is to find x that makes this true, but the way the technique we've learned on how to do that is to change the equation so that it's set relation to 0 and then solve from there. Because whatever the answers are to this question are also the answers to this. Okay? So let's do that. We're going to do quadratic formula with those. I am just going to try and remember. So if you're going to type it in your calculator, students, then you're going to say x equals negative b, which is negative 1.75, plus or minus the square root of b squared, which is 1.75 squared, minus 4 times negative 1.25 times negative 3, all over 2 times negative 1.25, 0.125. Yeah, okay. So this is what you're typing in your calculator, right? And that's what I'm going to go do now. I'm just trying to not forget it. Okay, let's do this. Let's do it. Negative 1.75 plus or minus the square root of 1.75 squared minus 4 times 1/8 times 7 all over 2 times negative 1/8. Okay. Wait, it was not 7, was it, guys? It was 3? Hold on. So it was minus 3. I'm silly. It's negative 3 right there. There it is. 2. Okay, sorry. I was still thinking 7, but it's negative 3 is the C value, right? That's the C value. So I plug this into a calculator, and one of the answers I get is 2 feet. But then what's the other answer? Because you want to test both. Also, there's Rose's Cafe again. We're going to change this plus to a minus, and I get 12. Aha. And so this is 12 feet. So I have 2 potential answers here. Are they both the answer, or is only one the answer? And I'd say, well, think about this. So it's saying that it's going to happen at 2 feet or at 12 feet. But if he's standing at 2 feet, what that actually means is he's thrown the ball up, because this point is 2 comma 10. And then it comes down at 12 comma 10, right? So, assuming both of those are the hoop, apply realism to this. Is the basketball player shooting underneath the hoop, right? Because he's throwing up through the hoop? That doesn't really make a lot of sense, right? Makes a little bit more sense for him to be throwing far away and then it comes down through the hoop, right? Rather than throwing it upwards underneath the basketball hoop, right? So we're going to say 2 feet isn't really realistic. I mean, it could work if that's what you were interested in, but 12 feet makes the more realistic, logical sense answer, right? Unless, of course, he's allowed to throw from underneath the hoop. If this is allowed, then 2 feet is a perfectly reasonable answer, but I don't think that's how you play basketball. I think you try to shoot it from above the hoop, and there it is, 12 feet. Okay. Nice. All right, we've got one more problem. Example 3, which is an area model. Okay. So we've done a few, projectile motion ones, but this last one is an abstract question where the picture you draw and the thing you're seeing is not a parabola at all, right? So you're not seeing this parabola visually, but a parabola will kind of appear once you start doing the math. So it says this: the city of Round Rock is building a new playground on a rectangular pad. The pad being built is 10 feet longer than it is wide. Okay, first of all, I'm going to make a rectangular pad. Well, that's not a rectangular pad. Let's try that again. Nice. So there's my rectangular pad, okay? And it says it's 10 feet longer than it is wide. Do I know how wide it is? Nope. So I'm going to say, let's call this X. And then if the other side is 10 feet longer, then that's got to be X plus 10. Right? Okay. They are also building a sidewalk around the playground for parents to watch their kids play. The sidewalk must be at least 4 feet wide, or it must be exactly 4 feet wide to accommodate for strollers. So I say, you know what, let's lasso this. I'm going to take this with me. Come here, you. We're traveling to the other side of the page to get us some room. Okay, there we are. So there's my playground, right? And I'm going to zoom in here. I'm going to get a really detailed picture for you. That's X plus 10. Okay, that's kind of ugly. Do that again. X plus 10. Oh, much more beautiful. There's X. Ooh, let's do it on the inside. Okay, that's the playground. And I know it's the playground because... Because this is a playground because there's a child on a slide, and playgrounds have slides with children. So this is my playground, and around this playground is going to be a sidewalk, and that sidewalk is going to be, it has to, by the city regulation, be 4 feet on all sides. So I'm not going to do this about like that-ish. That's okay, that's not bad. So this rectangle is the sidewalk, right? So here's mommy with her little stroller. I mean, it could be mommy, or it could be daddy, or it could be daddy and daddy. Who knows, right? There it is. So and there's a little baby in here, right? Wah, wah. Okay, so that's my stroller. And this is the sidewalk all the way around. So, I say, if this is 4 feet in all directions, I say, that's 4 feet. And this is 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 4 feet. It is 4 feet in all directions on the sidewalk. So what does this mean about the exterior dimensions of the entire space? Well, this length is X. This length is 4. This length is 4. So then this is 4 put with X put with 4, right? Which means that this whole length on the outside is X plus 8. And then you could say this is 4, and this is 4, and this is X plus 10, So it's x plus 10 plus 4 plus 4. And so that means this whole thing is x plus 18. Okay? So I have two rectangles. One is x by x plus 10, and the other is x plus 8 by x plus 18. And this is just to visualize, the sidewalk and the playground kind of going around. Okay? All right. So write a function that represents the area of the sidewalk around the playground. Now hold on a minute. Think about that. The area of the playground is this area. This is the playground, so its area is this space. The area of the entire space is this whole thing. But what the question is asking me is to write a function in terms of x that represents the area of the sidewalk, right? So it's this border, it's this trim all the way around the rectangle. And you might say, how am I going to do that? Well, you think if you took the whole thing, right, which is all of it, and then you subtracted just the playground, right? So you took the whole thing, and then you just took away the interior playground, that would leave you with the space between them, right? The difference in that space, which is the area of the sidewalk. So, what's the area of the whole space? Well, area is length times width. And this length, this is the whole space length, is x plus 18, and this length is x plus 8. So, the way I say this, right? The area of the sidewalk is the area of the total space minus the area of the playground. But the total space is length times width, which is x plus 8 times x plus 18. Okay, as evidenced by the exterior side lengths right there. Minus the area of the playground. But the playground, again, area for rectangles is length times width. So it's this length, which is x plus 10, times this length, which is x. So to say this is minus x times x plus 10. So let's do a little bit of distribution here. X squared, 18x, 8x, 8 times 18. 8 times 9 is 72, right? And so double that for 18 is 144. And then minus x squared, then negative x times 10 is negative 10x. Now combine all our like terms here, you're going to notice something. This negative x squared and this x squared are going to actually end up canceling. And then this negative 10x and 8x are going to kind of cancel as well. Or not cancel, but they're going to combine. Actually, we have three things. 18, 8, and 10. So it looks like if I add all that together, then I just have 16x and then plus 144. Okay? And that works. Okay? And so that is the area of the sidewalk around. And it's just a function representing that. You might say, why is this important, Mr. Spake? I said, well, you could find, depending on however long you choose the park to be, this one might help you figure out the area of the playground, but also the area of what you need for the sidewalk, right? Also, if you kind of think about it, you could chunk these. Okay, but the way I just recommended and demonstrated, that's the way I recommend you do it on the test, should it appear on the quiz or test. However, here's another way to think about it. Well, let me do blue here, okay? This length is 4, this length is 4, and this width is x plus 10, right? So it's 4 times x plus 10 is its area. And similarly, this length is 4 times x plus 10, which if you distribute that, that's 4x plus 40, doubled is 8x plus 40, okay? Then you do the same thing for this length. which is x by 4. So it's 4x, and you do it here. That's 4x. So that makes another 8x. And then each of these little squares is a 4 by 4 square, right? That square, this square, this square, this square. They're 4 by 4s, so they're all of area 16, and you have 4 of them. So it's 4 times 16. So then if you total that, that's 16x plus, and then 4 times 16, let's see, that's 64. And so that's, oh, what? 104. 64 plus 40. I get 104? But didn't I get 144 over there? What's 8 times 18, guys? Okay, it's 144. Did I miss something? 4x, that's 40. Oh, that's 80. That's 80. Okay, that's why. Okay, so then that's 144. That was my mistake. So anyway, I'm just showing you that yes, indeed, the border does add up to that. And you could do that, okay? You could. It's not that hard. But, this is a neat way to do it too, taking the area of the total minus the area of the playground. Okay. Last question, then we're done with the video. Hooray. The budget for the playground allows for a maximum square footage of 600 feet squared of poured-in-place rubber for the base of the playground. What are the maximum dimensions of the playground that utilize the full budget? So what this means is we have enough rubber, right? Poured in place. You just pour it. The truck pours all the rubber, then it solidifies. Whatever. They spread it out, it solidifies. And we have enough money to do 600 feet squared. Now we could do 500 feet squared, but we have enough money for 600 feet squared. So ideally, we would like the area of the playground to be 600 feet squared, right? So what that means is this guy right here, area of playground, which is represented by this, we want area of playground to equal 600 feet squared. But the area of the playground is dimensions x by x plus 10. And so I say, okay, so distribute that. That's x squared plus 10x equals 600. And as we talked about just a little bit earlier in the video, whenever you're solving a quadratic equation, set it equal to 0. So I'm going to take this, subtract 600, like this, and you set that equal to 0. And then you could solve. And you could do quadratic formula, which is true. However, I did mention that in some rare cases, you're going to be able to factor. Maybe check that without just jumping straight to quadratic formula. Are there two numbers that multiply to get negative 600 that add to get 10? Sometimes students say, 60 and 10, but that makes 50, right? Then you say, what about 20 and 30? And if you made it negative 20, then this would factor as x minus 20, x plus 30, which will get you plus 10x and minus 600, right? That means the roots, or the answers, the solutions, are positive 20 and negative 30. But of course, negative 30 as a width doesn't make sense, so we reject that and say x is 20. But again, have we answered the question? What are the maximum dimensions of the playground? Well, x is 20. What's the other side length, according to my picture? X and x plus 10. So the other side length is x plus 10, and 20 plus 10 is 30. So the dimensions need to be a 20-foot by 30-foot playground. And that answers the question, right? If I had 600 feet of concrete, right, or not concrete, of rubber for the playground, then I would want to build a 20 by 30-foot playground because that would fully utilize that 600 feet. Isn't that nice? Cool. Okay, I think that'll do for the video. I know it was a long one, but it was a walkthrough for various types of different problems. Yeah. Again, when you're working through the homework, you might encounter revenue and cost, maybe some other types of area problems, right? All sorts of, who knows what you encounter on there. But just think, it's these three things, right? What is the minimum maximum of the parabola? When does it hit the ground? When does it equal to 0? When does it level out to 0, right? Or what is a point on the parabola, right? It's just, they're all parabolas, and you're just looking for points on them. That's it, okay? So connect that with the image and the thing you're doing. My recommendation is to draw a picture. Notice we had a lot of pictures in this. There's our brain. Our brain can develop pictures. We love it. We got a picture here. We got a picture here. Use your pictures. Connect the knowledge. You've got it. All right. I hope this was helpful. Thanks for watching, and I'll see you next time.